All right, in the last lesson we talked about converting exponential functions into logarithmic form. And in this lesson we're going to take a look at properties of logarithms. So let's just start that, and we're going to just recall some things. First of all, since a logarithm is an exponent, keep in mind that the two are going to be closely related. When I am multiplying numbers with the same bases, I can quickly do so by adding the exponents. And so again, since the logarithm is an exponent, the properties of exponents and properties of logarithms are going to be closely related. So in multiplying logarithms, the logarithms are going to be added. Okay, let's take a look at a few examples. All right, in this example we have the log base 2 of the factors a times b. And since these two numbers are factors and they're being multiplied together, then I can rewrite it like this. And this is called expanding the logarithm. And again, I want to bring back the fact that John Napier, actually, that was the purpose of doing this. He was trying to find an easier way to multiply two very large numbers, and so he converted them into addition problems. And that's the reason why logarithms were initially formulated. And again, it took him 20 years to make out these tables so that it could be done. In the next problem, we have three factors, 5, x, and y. And so we're going to have to expand it 3 times. And that's how it's written. In the next one, it's already expanded, and so we're going to take it back to its original form. And since we know when you're adding exponents, the operation going on is multiplication. And so that's the example for condensing is what that's called. All right, again, let's recall some properties here for exponents. When I'm dividing exponents with the same base, I can subtract the powers. So since a logarithm is an exponent, when dividing logarithms, the logarithms will be subtracted. And so let's take a look at these two examples. Notice they don't have any base numbers, so again, they're going to be common logarithms. We don't have to write the base of 10, and that makes it nice. All right, so this is our quotient. We have two components to it, so we're going to have two logs involved in this. So it's going to be log r minus log t. Okay. In this next example, we have 3 pieces. The first 2 are being multiplied, and these are being divided by z. And so this is kind of a combination. We're going to start with these up here. We're going to say log 2 plus log j, and then the rest of it is being divided, so we're going to put minus log z. All right, another property of exponents is when you have a power raised to a power. What this simply means is that I have 5 copies of this monomial. So I have 5 copies of 2, 5 copies of x squared, 5 copies of y cubed. And a shortcut I can take is just multiply those powers together. And so I'm going to kind of distribute this 5 to every power. It just saves me time. I could write the whole thing out, but it'd be very time consuming. And so guess what? When raising a logarithm to a power, the logarithm is multiplied by that power. Just like 2 was multiplied by 5, and 3 was multiplied by 5, and 2 to the first was multiplied by 5. All right. So here's some examples. All right, I like to call this the cut and paste rule because basically you're going to cut this off and paste it out in the front. And if you think about it, I have 5 copies of b, so I could write out b times b times b times b times b, and I could add them all together, and I'd have 5 copies of log base 7 of b. And this is just it simplified. It's just much quicker to do this little cut and paste rule. This one is a combination, so I've got a factor going on here. There's multiplication going on here as well as a power. So this is what this will look like. I'm going to cut and paste that 2 out in the front. I'm going to add because these are being multiplied, and I'm going to cut and paste that 3 out to the front. All right, just a little review on radicals. In Algebra 1, we can rewrite this without the radical. And when we remove the radical, the 2 is kind of understood to be there, but it's kind of hanging in midair. And so it takes a little road trip, and it travels to the denominator of this. So anytime you have a radical, you're going to convert it to an exponent. And now we can use our little cut and paste rule, and that's going to be 1/2 log x. All right, so if you have your calculator, you can follow along with this. I just want to kind of show you from the calculator's point of view that this system truly does work. So these 3 expressions are all equivalent to each other. And it's no doubt that 2 times 6 and 3 times 4 both equal 12. So if I calculate log 12, because it's base 10 in my calculator, I get approximately 1.079. Now let's just take a look. Does that mean that log 2 times log 6 equals log 12? And unfortunately it doesn't, and neither does log 3 times log 4. So what's going on here? Because logic would dictate that log 2 times log 6 equals log 12. But that's just not the case. Remember, when you're multiplying, you're going to add those logarithms together. So on your calculator, if you'll take log 2 and add log 6, you will get 1.079. And then in like manner, if you take log 3 and add log 4, you will get 1.079. Pretty cool. So adding when multiplying logarithm yields an equivalent answer. And log 12 is also equivalent to 24 divided by 2. And it's also equal to 36 divided by 3. So again, if we used our lack of knowledge and used a little bit of false logic and we divided these out, you would think that they would equal log 12, but they turn out to equal something totally different. Same is true for log 36, something totally different. However, if you subtract the 2, you will get 1.079. So again, this is just to show you that this system works. And we're going to, I'm going to conclude this video here, and we'll pick up with condensing logarithms in another video.